I'm pleased to welcome John Nielsen-Gammon to the podcast. John has been the state climatologist of Texas since 2000 and is also serving as a Regents Professor of Atmospheric Sciences at Texas A&M University and also Director of the Southern Regional Climate Center. So multiple positions. Not sure how you do it all, John. And he has received numerous awards during his career. And today I would like to emphasize the award he received from Sigma Xi for being an excellent communicator. And I'm sure we will benefit from that today. So thanks so much, John, for joining me.
All right. Yeah, you're welcome. My pleasure.
You've done a lot of different types of research on climate-related issues, John. And today I think we're going to focus on extreme events and talk about your recent presentation to the legislature after the Central Texas flooding, which was excellent. And then go to the other extreme, talk about droughts, and then also the report that you developed for Texas 2036 on climate extremes. So I think on top of everybody's mind is the recent Central Texas flooding with so many lives lost, about 117 people. And I thought your presentation to the legislature was very informative. I think you mentioned 10 to 15 inches of rain in Kerr County, resulting in flooding in the Guadalupe River. And I guess the intensity was 3 to 4 inches per hour. And you indicated that you didn't think it was possible to predict the location of the flooding 1 to 2 days in advance. And also that the weather warnings could not keep pace with the threat and change in action necessary with such rapid rises of flood stages in the river. So maybe you can describe a little bit more about the situation during the July 4th flooding in the Guadalupe.
Sure. Yeah, the setup that you need for very heavy rainfall in Texas is essentially, sounds obvious, but lots of moisture. But that means not just moisture at low levels, but also moisture higher up, because if you've got a thunderstorm developing, the dry air in the atmosphere will sort of choke it off and cause rain to evaporate before it reaches the ground. So in this particular circumstance, it's the summertime, so we've almost always got plenty of moisture at low level. But in the higher levels, we're talking like a mile up, 2 miles, even 5 miles, we had moisture coming from northern Mexico, which had gotten there through some combination of tropical storm and Atlantic and a hurricane in the Pacific. And getting that feed of moisture allowed the situation where you can get extreme rainfall. Of course, we had a extreme rainfall watch in place, but it covered lots of western and central Texas because there was a lot of moisture in that whole area. But what finally ended up happening, unfortunately, was that in a few locations, thunderstorms developed and were stationary. They didn't really move. For that to happen, you've got to have differences in the wind at different levels in the atmosphere that can sort of hold the storm in place while you're still getting a feed of moisture coming in at low levels. So that happened in like northern part of San Angelo. It happened in Mason County. It happened in Travis and Burnett County the next day. But the flood that killed most people was the flood in Kerr County, where thunderstorm just sort of developed and grew and stayed in place for several hours. So we had a sense that heavy rainfall is possible. The forecast really didn't mention the possibility of something more than 7 or 8 inches. That was a shortcoming in the medium range forecast, but then you can't really warn on the storm location until the storm actually exists and you see where that particular type of storm has developed. And so when that happened, they got the warning out fairly promptly, a little after 1 a.m. But unfortunately, the storm just sort of stayed there, and the update had a hard time keeping up with how much rain was actually falling. And I think part of the problem was the Weather Service didn't have a direct connection to the actual amount of water in the South Fork of Guadalupe until it finally reached Hunt and Ingram and moved down toward Kerrville where the gauges were located.
Right, yeah. And of course, being a holiday and then the storm starting in the middle of the night and all of those things, were difficult to deal with, but also, maybe some buildings in the floodplain and many different aspects. I thought it was interesting in your presentation to the legislature, you described many of the similar floods in the past to the recent flooding. And I thought that was very helpful to understand, this is not the first time. And when I was reviewing the various ones you mentioned, it's interesting how many of them occur on holidays. And of course, if they happened in the middle of nowhere and there was nobody there, it wouldn't be a problem. But so I thought it was nice to review the storms in the past and the flooding issues. So that was a good context, I felt.
Yeah, every flood is unique, so there are several different storms that have hit the high water marks at different points along the Upper Guadalupe. Probably the one that's most similar was back in 1935, which hit the South Fork pretty hard. And there were summer camps along the Guadalupe back then, but there was no loss of life with the flood. And part of the reason for that was it happened in the daytime where people could see the water rising. It was easy to recognize the hazard and get out of the way of the water. When something happens at night, you've got a lot less sense of what's going on. The heavy rain and lightning is very intimidating, so you're reluctant to get outdoors. So that was unfortunately one of the dominoes that fell that led to the catastrophe that we experienced. But even at that, there was 10 to 15 inches of rain there, but that pales in comparison to some of the other rainfall events that we've seen historically in the region. The one that actually is sort of record-setting on a world scale was over 21 inches of rain in less than 3 hours. So that's almost twice the rainfall rate that caused the Kerr County flood. So the floodwaters literally could have been twice as large if that sort of thing had happened in the wrong place and again at the wrong time.
And was that the one in Dehanis? Was that?
Yep, that's right. Yeah, the rainfall was measured at a ranch about 10 miles upstream of Dehanis. And by the time the floodwaters got to Dehanis, they were so big they actually overflowed into the next creek over.
Right. Yeah. And I guess some of the others that you mentioned, the 1921 storm in Thrall, Texas, in September, 36 inches of rain in 18 hours. And that impacted Austin and Thrall. And that was, you mentioned that was a U.S. record, I think.
Yeah, it was a record for a while there. And the same event caused flooding in San Antonio, and basically the reason or motivation, at least, for the implementation of the flood control system that's in place now, which includes the Riverwalk, which is probably the second most famous aspect of San Antonio these days, behind the Alamo, which we all remember.
Right, yeah. So we're no stranger to these extreme events, and I guess the state is doing more and more on flooding. Texas Water Development Board has the flood planning efforts and trying to map the 100-year, 500-year floodplains and do a lot of modeling analysis and bottom-up approach. So it's nice to see that. And you are currently doing a study for the Texas Water Development Board, collaborating with Rice and other groups, Rice University, on extreme events and rainfall return periods. Can you describe a little bit, the methodology you use to do that type of work? And I know you mentioned that the work should be coming out in the fall. Your publication should be coming out this fall.
Yeah, it's been about almost a 3-year project at this point. The And the basic idea is that we have seen across most of the United States, including Texas and the Gulf Coast region, an increase in extreme rainfall. And most of that, if possibly all of it, is due to the rising temperatures that we've also experienced both locally and in the Gulf of Mexico and globally. That leads to warmer temperatures in the atmosphere, which increases the capacity of the atmosphere to hold water. And that means that a given storm system will end up producing more rainfall at a greater rate. Of course, you can also get changes in where the storms exist and changes in storm structure with a different climate. But that seems to be the temperature thing seems to be the main factor driving the increase across the southern United States. So the federal government's looking at that sort of stop-start with the Trump administration, but they've made a lot of progress in analyzing trends in rainfall, extremes, and looking at climate model projections. But we're following a somewhat different approach than they are. They're treating the trend as the historical trend, and whatever that is locally, that's what's been happening historically, and then they patch on to that the projected trend from climate model. But a couple of problems with that. First off, you can't really trust local trends. I talk about rainfall extremes increasing overall. You can only really tell that if you look at trends over a fairly large area, because the randomness of the weather, we call it natural variability, can affect a trend locally. There's a big difference in the extreme rainfall trend between, say, Houston and Victoria, because Houston has had Harvey and Allison and Morley flood, et cetera, et cetera. But there's nothing special about the climate of Houston compared to Victoria that would make things happen in one place, but not the other. So local trends we don't think are as reliable as larger scale trends. Second difference, the historical trends tell us something about the future trends, right? Models aren't perfect. So looking at what's happened historically gives us a clue as to what to expect going forward. And likewise, even though the models aren't perfect, you can run lots of models and average out natural variabilities. So they help to tell you what the climate change signal might have been historically. So rather than looking at those two periods separately, those two information sources separately, we're merging that information and getting what we consider the best estimate of both the historic and future trends that are consistent with each other and consistent with the other estimates of extreme rainfall that we're producing from the data. So those are the main differences. We're right now we're finalizing that merger process. So we expect to see some numbers preliminarily within a month, and once we trust them, we'll deliver to the Water Development Board, and they'll be available for use for people who want to take that into account. Important thing to remember is it matters not just for the future planning, but also affects the present. If extreme rainfall, for example, is increased by 10% over the historical period, if you don't take that into account, then your estimate of extreme rainfall at the beginning will be 5% below what it really, 5% higher than what it really was. And at the end of the period, the present day, it'll be 5% lower. So we're already, by not taking this into account, underestimating flood risk. And that underestimate only gets worse in the future. So we're going to try to make sure that we've got something more reliable than just the assumption of a non-changing climate.
Well, that sounds fantastic, John, and I'm delighted, that it's so data-driven, and then also, using the historical records and optimizing the modeling and the observations to have a consistent view. Because I think people, if you can talk to them about what has been happening, and that will, amplify in the future, then I think maybe they will have more confidence in it. So I'm looking forward to seeing that information. So another thing that you mentioned in the legislative presentation was that flash flood warnings in Hunt, Texas, downstream of Kerr County floods, that there were about 110 of those over the past 23 years. And so maybe people get a bit immune to these warnings. And then also, I think you were emphasizing that warnings need to include some indication of action. Should you stay where you are? Should you go to higher ground? When should you do it? And in order to have reliable forecasts, in order for people to take heed of these things, they need to be the forecasts need to be reliable. And so I'm just wondering, do you think we have the skill to suggest actions and to improve the warnings? I know from my own experience after Hurricane Rita, a lot of people moved out of Houston and came up to Austin, and I was in a wreck that weekend, and the person behind me had just come from Houston, and they were complaining that their wife made them move, and then they ended up being in a wreck. But also, just looking online, they said 100 people died, and it was a deadly evacuation. So it's a difficult process, and a lot of psychology and other things involved. So, what are your thoughts about that?
Right. The whole point of National Weather Service issuing a warning is because there's something going on that people ought to pay attention to and may need to act on. Right? If there's a tornado coming, find a secure place, take shelter, that sort of thing. But on the other hand, as a society, we sort of push back on rules and being told what to do. We like to make our own judgment. That's certainly true for me. If I see a tornado warning for my area, I'm going to look at the radar, I'm going to look out the window, and I'm going to figure out what I think is happening. Of course, I've got the scientific expertise to be able to make good judgments on that, but it's a natural response for people to not necessarily trust what they hear, especially if it's a non-specific sort of information. And the National Weather Service for flood warning is issuing a warning for a substantial part of Kerr County, in this case, 100 square miles. If anybody who traveled in the hill country knows, there's lots of what we call low water crossings where there's the road is designed for the floodwaters to go over it rather than under it, rather than building a large bridge. So if you've got a minor flash flood, the appropriate action is to stay put, not drive, not risk getting washed away at a low water crossing. If you've got, though, a major flash flood that only one out of the 110 warnings that we've had in the past 20 years, and then the proper action may be to get to higher ground. But it depends on where you are again. If you're not at risk from the flood, you should stay put because the lightning is a hazard. So that sort of information is not something that a typical weather warning can possibly convey. They can give blanket advice, but the information that's really needed for action is very location specific. So, I could, on the one hand, that could be handled on an individual personal level by people being very aware of what their flood risk is in a given place, and understanding what's possible. But that's the challenging things to do, to be aware of whatever hazard is and what every action should be at any given level. So I think where we will move to eventually, not in the next couple of years, but eventually, in addition to a better mechanism of getting the warning out to people through sirens or whatever, is personalized warning, where your cell phone knows where your location is. That includes your altitude. So the height above the river is something known by technology, and potentially a flood warning can provide the information as to what the potential height of the river is, and your weather app could translate that into you need to find a place that's at least 10 feet higher than where you are, for example. Sort of personalized weather warning, very location specific. We don't have such a system in place, but other than making sure we have adequate cell phone coverage, there aren't actually any technological barriers from making that sort of thing happen. So I'm very optimistic that we'll solve that problem in the next decade or so.
Right. And I think, you mentioned people being aware of the hazard, their risk from floods and stuff like that. But when I was reviewing when the floods happened in the past, a lot of them happened during holidays. And so people are visiting, like the Wimberley floods and Memorial Day, the recent July 4th flooding. And, but I also heard about Norfolk, Virginia, in the Waze app. It provides information on, you shouldn't, what roads are passable or things like that. And then the drivers then confirm or send feedback back to the system. I don't know much detail about it, but it also includes tidal issues and things like that. But I agree, but then if you lose cell coverage, then you're, in deep trouble.
Yeah, I mean, we could do a lot with local monitoring also. So not necessarily relying on an accurate warning. If you know that the water is within 3 feet of your foundation, there's a risk. And there you don't necessarily need a high technology solution for that sort of thing. There was at the same hearing in Colonel, one of the survivors of the flood testified that she was awakened by an alarm going off, and that alarm was their water softener system, which had a leak detector. Except in this case, it wasn't detecting a leak; it was detecting the fact there was water covering the floor of their house already, and that probably saved their lives, and possibly the lives of some of their neighbors. So, as long as there's some way to you get the information of what's going on, it doesn't need to be from the weather service to emergency manager to an app to the phone. It could be something very simple, but the problem here was people did not have that information through any mechanism, and they were asleep until it was too late.
Right, right. And another thing that you brought up in the presentation to the legislature was the need for increased monitoring and the very limited monitoring you described early on about these systems that come together, per current. They were like, tail of a tropical storm and then a hurricane from another region. And you indicated that some of the monitoring at Del Rio, which is 700 miles away, was very helpful. And there's a lot of uncertainty where the storm is going to happen. And so having more monitoring at the border because a lot of systems come from Mexico to the US, or, maybe you can elaborate on that, John.
It's a sort of a weird thing with the atmosphere where you can get by with relatively far apart observations of wind and temperature and pressure because all those factors are tied together, and it's possible to figure out what's going on in between. But the water vapor, the moisture in the air, doesn't behave like that. It can have a lot of fine scale structure. You can see that if you look out the window and you see clouds in one place and not another, and and in this case, it was where the moisture was largest that presumably made all the difference. And in the West Coast, they have sort of a similar sort of problem because they get their rainfall and their flooding from what are called atmospheric rivers, large plumes of moisture that are fairly narrow. They're coming in from the Pacific, and you don't have any weather balloons upstream over the Pacific. Back in the 60s and 70s, there actually used to be one or two ships stationed out in the middle of the Pacific Ocean for the purpose of taking observations and launching weather balloons, and that was very expensive. They stopped doing that when they got satellite, but you sort of lose the ground truth information, the direct measurements of what's going on. The view from satellites is fairly blurry. So they've tried to solve that problem by not only sending out aircraft to make monitors, but also basically putting up a sort of a fence line of observing systems, measuring the wind, measuring the humidity, and so forth, that they can't rely on upstream observation. In Texas, we have sort of the same problem. Half of our incoming air during a rainfall event coming over the Gulf of Mexico, where we don't have any observations of what's going on above the sea surface. And then half of it's coming from perhaps northern Mexico, where there are observations, and we help subsidize them, but they're not as reliable. There were a couple observations missing in key areas. So that means between Brownsville and El Paso, there's only one reliable upper air site, and that's the one at Del Rio, like you mentioned. So potentially we can do much better by having just 3 or 4 additional observing sites along the Rio Grande. Probably want to add 1 or 2 along the Gulf Coast as well. And before we just go in and commit to those observations, it's possible to actually run simulations of past weather events and see what sort of impact those types of observations would have, and essentially figure out, well, what do we get the best bang for a buck? Where can we get observations that would actually provide key information, and how much information we need? Maybe I'm wrong, and we actually wouldn't have done better because it's just too chaotic a system, but we can actually test that out and make the investments to save lives and provide more advanced warnings of the potential for very heavy rainfall in areas larger than just, or smaller than just west and central Texas.
No, I think that would be fantastic, and I agree. To use modeling then to try to target optimal locations and see how much you would have benefited from that additional monitoring. That would be very good analysis to do. And so jumping to the other extreme, droughts is the other thing that we often experience in Texas, and I guess the 2011 drought was the worst one-year drought in many regions of Texas, when most of the state was in exceptional drought. Maybe you can describe a little bit, John, the development of that drought. And I know Nell Fernando and her colleagues did a nice paper on what caused the intensification of the drought, and then the following winter in 2011, the demise of the drought. But and I also was looking at, it's very obvious the impact of that drought, and for the next until 2014, you could see it in the reservoir data and Texas Water Development Board water data for Texas, which I think is best thing since sliced bread. You can see the historical reservoir storage, so it's very interesting. So maybe you can describe a little bit about that. Yeah,
I love that website too, waterdatafortexas.org. I use it all the time, and you can look at current reservoir levels. You can look at how they've changed over the past year. You can look at historical patterns and so forth. And if you do that, you look at a reservoir in West Texas, you see that basically the waters are dropping most of the time, but every once in a while there's this big upward spike when there's a heavy rainfall event or a flood that causes levels to rise, or maybe even fills up the reservoir. In East Texas, you get a fairly different picture. You see the reservoir levels going up and down, always staying pretty high. Frequently, they're stuck at the storage capacity. So in a sense, what that amounts to is normal rainfall in West Texas corresponds to a decline of water supplies, whereas normal rainfall in East Texas is perfectly adequate to maintain supplies under the current amount of water use that we have. So for a drought, obviously a drought starts when it stops raining. People talk about drought early warnings, but that's pretty challenging to actually pull off, because you don't know that it's going to stop raining for 2 months until it has stopped raining for a month or two. Maybe after a month and a half, you can say, we're reaching the point where we might start seeing impacts agriculturally and so forth. So at least the agricultural warning levels might be useful in forecasting, but you really can't do much better than that. Our main tool for long-range forecasting has historically been looking at things like El Nino and La Nina. Those are temperature patterns and weather patterns of the tropical Pacific that affect our weather because they're affecting mainly the strength and location of the jet stream. With an El Nino, the jet stream is farther south. We tend to get lots of rain during the wintertime. A La Nina farther north, so we tend to miss out. So in 2010, 2011, that was a La Nina year. It was a stronger La Nina than anything we've seen since then. And that tends to lead to drier than normal conditions. And it definitely did in this case. It probably accounted, if if you knew it was going to have that big a La Nina, you probably would have expected rainfall totals to be maybe 20 or 25% less than what they normally would be. It turned out rainfall totals were 50 or 60% less than what they normally would be. So that low a rainfall amount probably couldn't have happened without a La Nina, but it also wasn't guaranteed with a La Nina. It was unusual even in the context of a La Nina event. And then in the spring and summer, you get this sort of feedback mechanism in place where if there's not much moisture available in the ground, there's not much moisture that can evaporate into the air, and you can't really feed thunderstorms. And if the drought extends into northern Mexico, then the air aloft is going to be dry also because the air's coming off the plateaus and essentially preventing thunderstorms from forming, putting a lid on convection. That's a fancy scientific term that we actually use, lid. It means what it says it means. It's basically area that wants to rise can't because it hit warmer air aloft and ends up sinking back down. So you can get that self-perpetuating process. And again, that contributed to it, but also the bad luck of the weather circumstances contributed also. So for the first few months, the impacts are mainly agricultural. The land surface dries out fairly quickly. Fortunately, it started in the cool season, so it didn't dry out much. But by the time we got into the spring, things were pretty dry, and normally you'd be getting lots of rain then, but we didn't get that. As the drought persists, then you're having reservoirs being drawn down, and then you start getting what we call a hydrologic drought, where water supplies are affected. For surface water, it generally takes a year or two because usually we've got a several years water supply in any given reservoir. For water supply droughts with real groundwater, it's actually, as you know, a bit different. It tends to be sort of a capacity-driven drought where people need to use more water to irrigate the landscape, irrigate their gardens, and the pumps just can't keep up. And if some pump goes out of commission, suddenly you're left with a water shortage. So it was a very fast developing drought. Then the water shortages kicked in, and in much of Texas, the reservoirs didn't fill up again until 2015, even though we had fairly normal rainfall in 2012, 2013, 2014. 2015 was the exceptional event that caused flooding and caused the reservoirs to fill up. The Wimberley flood was the most damaging flood, but there was massive rain in many other parts of the state. In fact, the month of May 2015 as a whole was by far the wettest month on record overall for the state of Texas. And that basically ended the drought. We had a hot summer, a dry summer, and then another wet fall. And, it's the story of the weather in Texas. You got drought, then you got floods, then you got droughts, then you got floods. Sometimes you have them both at the same time.
So yeah, I think that is fantastic. And another website that I also really like to look at is the U.S. Drought Monitor, and we have the Texas Drought. Also, the Water Development Board hosts the website on the Texas drought. And what's really nice about it is that you can see the long-term context. How bad is this drought relative to previous droughts? And so if you look at the data for Texas as a whole, you can see 2011 was off the scale, but then the drought persisted until 2015. And so a colleague, Mike Dettinger, has written a paper about the atmospheric rivers in the West and talking about drought-busting floods. And you said you normal rain maybe 12, 13, 14, but you didn't fill up the reservoirs because I guess the soil moisture, the soils were so dry that they just absorbed any water, and so the runoff was limited. And then you need an extreme event almost to overcome that long-term deficit. And so
we seem
Mike
to see
talks
the same
about
thing.
Drought-busting floods. Yeah,
we seem to see the same thing just recently. Right, the Highland Lakes, Lake Buchanan, Lake Travis, along the Texas version of the Colorado River, they were very low. They were somewhere between 25 and 50% of capacity, even though rainfall in those river basins have been close to normal. But it seemed like it was basically a lot of light to moderate rainfall events that soaked into the ground rather than any heavy events that ran off and filled the reservoir. They with the heavy rainfall in July, that problem was solved basically, as well as some stuff in June. So they got enough rain to end the flooding. And unfortunately, you can't rely on a flood because the timing is so erratic. I think of much of West Texas is playing water roulette if they're relying on surface water supplies, because you've got the weather has this gun that is firing bullets, and sometimes those bullets hold water, but most of the times they don't, and you never know when you're going to get the right bullet, is what it amounts to. We participate in the U.S. Drought Monitor development, by the way. We have weekly conference calls where we coordinate input to the Drought Monitor and give our representation as to what we think conditions are like based upon numbers we can point to, like rainfall's been low for the past 2 months, as well as our knowledge or information from on the ground of what sort of impacts are happening, like difficulty with crops growing or the water levels or stream flow or that sort of thing. And as part of the Southern Regional Climate Center, we're expanding our tools for monitoring that. Pretty soon we're going to go live with a tool that separates out the rainfall into the amount that's contributing to runoff and the amount that's soaking into the ground, so we can sort of differentiate between the rainfall that's great for agriculture and the rainfall that's great for water supply, and look at those things in a historical context. So we're looking forward to rolling that out in the next month or so.
Oh, that's fantastic. And is that based on intensity then and the antecedent conditions? I mean, if it's been dry for a while, then, some of those soils might be like cement, so it might run off. And, so I bet it's pretty tricky.
Yeah, I mean, we're doing a crude version where we're just sort of assuming a sort of a standard typical type of soil. But we'll have the hooks in place to really tailor it to individual locations as we move forward. But yeah, it's based upon something that's developed by U.S. Department of Agriculture for the sake of understanding how much moisture is available for crops. And so the idea is a little bit of rain doesn't help anybody. It gets the top of the soil, gets the leaves, and then evaporates. Then you get some rain, and depending on what the soil type is, most of that's going to soak into the ground, but then the more rain you get, the more it's going to run off. And if you've had rain within the past few days, then the greater fraction is going to run off and so forth. So it's not running a full-blown land surface model. People do that. We have that information that's available from other sources as well, but this is a way of just taking the rainfall and at least getting an initial estimate of what that means for runoff and for soil availability. And when we were testing it out last year with Hurricane Helene, we could really see the difference because they'd had drought in the southeast United States. And then Helene came on, and you look at the total numbers and see rainfall is back to normal. But the trouble is with Helene, it all fell in less than a week and most of it ran off, and the deep fill didn't really get replenished. So by separating out these factors, we can see those sorts of things that just the raw numbers don't reveal.
Right. And so that's really wonderful. And looking at the U.S. Drought Monitor, 2011 through 2014 and then 2015, it really ends abruptly in May 2015 when you look at the drought records. And I often see that also in the West Coast. They'll have a severe drought for 3 or 4 years, and then it'll end overnight because they'll get a family of atmospheric rivers dumping rain on them. So that's very interesting. And then after chatting with you the other day, John, and you mentioned that the Highland Lakes had filled up, then I went back to look at that and saw, they're up 80-90% full after the rains in July. So that was very interesting. I saw another presentation that you gave online on drought in 2023, and You described the drought being initiated by a heat dome, and also described the implications for future droughts. And you mentioned this Palmer Modified Drought Index. So maybe you can tell us a little bit about that.
Sure. Yeah. It seemed like 2013 was going to be a nice wet year. At least it was wet through May and early June. But what seems to have happened, and we're starting to see research getting published that looked at this, is we had this weather pattern set up in the second week of June where storm systems were carried away from the state, and we had a lot of air sinking and warming, and we basically had a heat wave. And if you look at the data, and maybe even remember it was only a couple of years ago, it started off very humid. We were seeing very high temperatures and high humidity. So it was quite uncomfortable, quite dangerous. As it lasted a week or even 2 weeks, the humidity started declining. So it was still hot, but it wasn't as humid. And, that was great for human comfort, but unfortunately it's a sign that the system, the land surface, vegetation is running out of water because the plants are not able to transpire, utilize water as much as they could before because they were running out of it. And as a consequence of that, there's this feedback mechanism can take place where you don't have water available in the atmosphere to produce rain. But another consequence is the energy coming from the sun. If there's plenty of water, it'll mostly evaporate that water and keep temperatures relatively mild. But if there's very little water available, the only thing that energy can do is raise temperatures. So when we have a drought, during summertime, we almost always have unusually high temperatures at the same time, and vice versa. This year, most of the state had plenty of rain during the summer, and we also had relatively mild temperatures. In College Station, where I live, we actually managed not to have any days over 100 degrees, which was nice. It was the 2023 was this sort of unusual setup where a temporary weather event in June had really a lasting effect on our drought situation until temperatures recovered in the fall and rainfall recovered. But that's part of why it's really hard to forecast out, because until that weather event looked like it was developing, maybe a week in advance, it was looking great. We were going to have a great summer.
Right. And so this heat dome then amplifies drought. I haven't heard that expression used very much, a heat dome. And then the Palmer Modified Drought Index. How did you modify the Palmer Drought Index to get better data?
Well, we didn't modify it ourselves. It's actually an official index. The Palmer Drought Index was originally created essentially. It was developed using drought in Kansas. It was designed to be fairly universal, but it didn't necessarily take into account how drought develops at different speeds in different locations. It didn't necessarily take into account how the impact of temperature on drought and evaporation is different in different locations. And so various different versions of the Palmer Index have come into existence in recent years and recent decades to try to deal with the shortcomings of it. And one of them is called the Palmer Modified Drought Index. And there's a hydrologic drought index. There's a Z index, which sounds kind of like a Marvel Cinematic Universe index for superheroes. But in any event, there's multiple ways of measuring drought, and you need multiple ways because drought impacts different things differently. If you have dry conditions during a certain 2-week period during the development of corn, it'll impact the yield, whereas other drought during other periods don't. So it's really very situation specific, location specific, and it's definitely not there's no perfect index, and there never will be.
So another source of data that I really like is these reports that you guys put out at Texas A&M. I think it's the Texas Water Resources Institute, and they're titled TXH2O reports. And they had one on drought, and they had a timeline of all the droughts since the early 1900s. And I really like those reports. So mentioned different droughts, and I was looking at each of the droughts that they described, and then looking at the annual precip data for the state. I know this is a very crude analysis, but I mean, there was like 1915 to 1918 drought, and then 1919 was a very wet, and USGS Water Watch data had very high runoff after that. And the same for other droughts like 1938 to 1940. Then 1941 was the wettest year on record in Texas, and runoff was also extremely high. The 50s drought that most people are familiar with, 57, was very wet. So this sort of thing. So do you think, how is there any way to predict when a drought might end, and or when we might go from a dry to a wet period, or a wet to a dry period, or what we could do to try to improve that skill?
Well, I mean, we can hope for the end of a drought, and if we have something like an El Nino, which tends to lead to weather with normal conditions, then we can maybe even bet on the end of a drought. But because of the importance of flooding and ending droughts, especially water supply drought, it's a big challenge. We didn't know where the drought would be improved in July 2025, even 2 days in advance. And after July 2025, the drought was it was almost fall, shall we say, along the Colorado River. It was improved a bit near San Antonio, farther west. Some of the rivers there that provide water for the Winter Garden area and for Corpus Christi, they hardly got an uptick at all. So the same challenge in forecasting plant flood applies to forecasting end of drought, because they're often the same thing. So I'm going to remain pessimistic about forecasting end of drought more than a week in advance.
Okay. Well, we can keep trying, I guess, and we can look at past records or whatever. But another report that you did recently, the assessment of historic and future trends of extreme weather for the Texas 2036 group. I really enjoyed it. I thought it was comprehensive, informative, and very balanced. And maybe you can describe a little bit about what you learned from doing that report, and why 2036, and a couple of things like that.
Yeah, thank you. It's sponsored by the organization Texas 2036, which is interested essentially in long-term planning and solving long-term issues for the state of Texas and its prosperity. And so part of that is understanding whether we're going to have to deal with different types of weather hazards or levels of weather risk in the future than we do in the past, for water supply and all sorts of other reasons. So they contacted me several years back to essentially do an analysis of historic trends, and we've updated a couple of times since then. They wanted to focus on 2036 because it's in their name, and it's in their name because it's the bicentennial of Texas independence. But it also is a convenient, it's only 10 to 15 years in the future, depending on which report we're talking about. And that's about the limit you can safely extrapolate trends on their own without relying more and more on climate models for projection. And they had a suspicion, which I agreed with, that a lot of Texans are suspicious of climate models and would think find observations to be the most reliable, so we wanted to focus on that. Of course, I myself as a scientist am able to look at climate models and see what they're saying and understand the reasons for them. So we, under the hood, we double checked and made sure that the trends that we're seeing were consistent with what projections would show. But we looked at basic temperature and rainfall, but then focused on extreme weather, extreme temperatures, extreme precipitation, tornadoes, hurricanes, floods, etc. And, we can say, you often hear in the news, the blanket statement, extremes are getting worse. And people tend to think that either means all types of extremes are getting worse, but that's obviously not the case. Cold extremes are getting better because temperatures are rising, so they don't get as cold as they used to. There are other types of extremes. Tornadoes is my go-to example, where we really don't have much of a clue whether they have changed in the past, because our means of estimating the number of tornadoes and their severity has changed so much over time. 30 years ago, people tended to flee from tornadoes rather than chasing after them. But nowadays, in the era of social media and so forth, people make a living chasing tornadoes. So it's pretty rare that a tornado gets missed, not observed. So the number of tornadoes has increased tremendously in the historical record, but the actual number of tornadoes in the atmosphere probably hasn't, or we don't really know. Conversely, if you look at tornado severity, the raw numbers say that severity of tornadoes has declined over the past few decades. But the way we estimate severity of tornadoes is by the amount of damage they produce. And one thing we're pretty good at as a society is learning to correct our mistakes. And if a tornado causes a certain type of damage, well, let's reinforce the roof. Let's make our buildings stronger. Let's not be as vulnerable to tornadoes. So we expect the amount of damage from tornadoes to go down, even if the number of potentially damaging tornadoes stays the same. So in our report, we look at all sorts of types of severe weather, and some of them we can say, yeah, this is happening. And others we can say, it might be happening. And others we say, well, we've got a few hints as to what might happen, but that's about it.
I really enjoyed the report. Temperatures are rising, and you explained that in a very simple way that people could understand. Is the number of 100-degree days doubling between now and 2036, and with a small increase in temperature, so I think people are aware of that, and so that's a nice way of describing the temperature changes.
The 100-degree days are not just, that's not just large-scale climate change. We got the heat island effect that contributes to that. Where people live, there are more people. You've got less natural vegetation. You've got people generating heat for your air conditioning. Air conditioning cools inside, warms up the outside. So on the one hand, we ought to include the heat island effect and just look at climate change. But what we're looking at is what people actually experience, and that is climate change plus the heat island effect. So both of those are contributing to the number of 100-degree days doubling, tripling, even quadrupling over several decades at the current rate of increase.
Right. And what was nice about the report also, is the estimation, the frequency of extreme rain, you say 10 to 15% increase relative to the last couple of decades. And so it's nice to put things in context. So the report is excellent, and I will include a link to the report on the website and to other papers that you have done, John, to provide information related to these. But also, people normally say everything is getting worse, so I really like your balanced communication style. So extreme weather in the winter will probably be less because of the temperature increases. it seems like we never hear about anything improving very much. So it's nice to have the balance. And the drought, and so moisture deficits, temperature linked to those, the higher temperatures. And you nicely explained, even if precipitation is not changing so much, so the soil moisture is lower, there's larger soil moisture deficit, so droughts will maybe amplified.
Yeah, the not total amount of rain is a sort of a big wild card because climate models don't all agree on the trends in Texas, and it's not really tightly constrained to simple changes in the climate system. But sort of the other things going on are pretty more obvious, like rising temperatures means that you have greater evaporation rates, and drought can develop faster, and impact, especially for soil moisture, can develop sooner and persist longer. So even if rainfall stays the same, we expect to see worse droughts and more frequent drought. The impacts of that may vary also. Climate change, carbon dioxide increases can make plants more resilient to, more efficient in using water, but they might just end up growing more, and then the bigger plants are just as vulnerable in the future as the smaller plants were today. So who knows what's really going to happen, but at least we can look at some of the factors involved.
Right. Well, thank you so much, John. I know you have about 3 different jobs that you manage, and I really appreciate you taking the time to talk on the podcast today. John Nielsen-Gammon is the state climatologist of Texas and Regents Professor of Atmospheric Sciences at Texas A&M and director of the Southern Regional Climate Center. And I think you will understand why he gets the award for being an excellent communicator. So thanks a lot, John.
Well, thanks very much. My pleasure.